All right, my children, here comes section 511. We're going to build on what we were talking about in 510, and we're actually going to solve these, and we're concentrating on these last couple steps. We looked at the first three steps in section 510. We're looking at steps 4 and 5 for this section 511. So we're going to be concentrating on determining a maximum or minimum value using calculus, and then making sure that the domain, the endpoints of your equation, actually represent the maximum or min. So determine the domain or endpoints of your equation to verify the endpoints represent a max or min. Pretty much here's the deal. We're going to take the equations that you came up with in section 510. We want to find a maximum or minimum, so that comes off the first derivative. So we're going to take the derivative of the equation that you came up with, set it equal to 0, and figure out where the maximums or minimums are going to be. So that's really the extra steps that we need to take to make it, to actually solve the problem out. Okay, so some of this information comes from what we learned in section 510, like this first one, number 1. So we already figured out what the equation was for this. Was this a distance thing? We want to know what point on the graph of the square root of x is closest to 5, 0. So if I were to guess, my guess would be maybe in this neighborhood. But that's just a guess. I don't know. Let's see what it's going to be, what the coordinate would be. All right, the distance equals, we came up with this formula in the last section, x minus 5 quantity squared plus x. That was the distance formula that we said was going to be closest to this 0.50. So this comes from, maybe we want to make a note, from 510. I get that. So you did the work for that already. So here's the extra steps. I want to find the one closest. Well, closest is like a minimum. Right? I want the minimum distance. I want what's closest. And so what I need to do to find a minimum is take the derivative of this piece right here. Now remember, I'm going to rewrite it before I put the derivative thing in. This is the same thing as, now you can do this a few different ways, but x minus 5 quantity squared plus x to the 1/2 power. You're kind of setting it up so you can take the derivative. Could you square it out and then add the x in and then do it? Absolutely you could. We're going to keep it like this and try it this way. So here I want d prime, distance, the derivative of distance. So if I look at this, the 1/2 comes down in front. The group x minus 5 squared plus x has to go to 1 less power, negative 1/2 power. And then I need to take the derivative of what's inside. Now that gets a little bit tricky because the 2 comes down, the x minus 5 goes to 1 less power, so it's going to be a first power times 1, the derivative of x. So there's the beginning of it. And then the derivative of the x is a 1. All right, so let's see if we can do anything to make this any better. Right, if I look at this, this is 2x minus, if I distribute this out, I get 2x minus 10 plus 1. So this is going to be a 2x minus 9. I know I have a fraction because I've got a negative power, so it looks like this. Now we're going to be taking this thing, it's going to have a fraction. You have a 2x minus 9 as your numerator. And in your denominator, you have this 2 from the 1/2, and you have this old crazy square root thing. Now you can write it as a square root, you can write it as 1/2 power, whatever you want. X minus 5 squared plus x. And that's what it looks like. That's what your derivative comes out to be. And you're like, holy moly, that's a crazy derivative. But what I want to do is take that derivative and set it equal to 0. So if I take it equal to 0, 0 equals, maybe I'll do it from the back end here so I don't have to rewrite it since I don't have a lot of space. I'm going to take this thing, I'm going to set it equal to 0. And if you remember that with fractions, It actually is like 0 over 1. I can cross multiply. It comes out kind of pretty because you just ignore the denominator. So if I have 0 over 1 and I cross multiply, it gives me this. 2x minus 9 equals 0. All you end up with is the numerator. And so swing the 9 over, divide by 2, you get 9 over 2. Well, darned if that isn't awful close to where I said. That's 4.5. So 4.5 was my guess where like this point would be, and sure enough, that's about where it was. Let's make sure that we answered the question. That's kind of one of the things that kids forget. Oh, I got the answer. I got x equals 9/2, but that's really not necessarily the answer. What point on the graph is closest to? Now, they mean a point is a coordinate. So I literally need an x value, 9 over 2, and I need a y value as well. Well, the y value comes from the square. Y is the square root of x. Well, what's x? X is 9/2. This would be the square root of 9/2. That comes from y equals the square root of x. And so now I have a coordinate. Now I have a point, and that's my value for that one. So that's number 1. All right, number 2, again, this one comes from our 510 notes. We came up with this example, with this equation already. It is this. It is big and ugly. It is the square root of 28 squared plus parentheses 30 minus x squared plus another square root. There were 2 pieces of wire. This was the wire guy. 12 squared plus x squared. All right. So what we need to do is find the derivative of this thing. So where should the stake be placed for the least amount of wire? So again, I'm looking for a minimum. If I'm looking for a minimum or a maximum, it's taking that first derivative and setting it equal to 0 and seeing what's going on. So I need the derivative of these things. Now remember that square roots are like 1/2 powers. Woo-wee. W prime. So I would have 1/2. I would have 28 squared plus parentheses 30 minus x squared to 1 less power, negative 1/2, times the derivative of what's inside. So inside at 28 squared, that's a whole number, so that's going to be a derivative of 0. But this thing, bring the 2 down, and I'm chain ruling this. 2 times 30 minus x times the derivative of what's inside of that, which is a negative 1. Whoop. Before we get to the second fraction, let's see if we can put this together, or the second piece here. Let's see if we can put this one together with where I'm at. So I have a fraction. I know that because I've got a negative exponent. I have the 1 over 2 gives me a 2 in the beginning. This whole thing is a square root in the denominator. We can square root it. You can write it as a 1/2 power. Doesn't matter. 28 squared plus 30 minus x squared. Okay, so that takes care of this piece. It's down the bottom. This piece here is going to be 60 minus 2x, but times a negative 1. So it's going to be a negative 60, and it's going to be 2 times negative x times a negative 1 is plus 2x. That's in the numerator. Could you cancel the 2, like take the 2 out and cancel it? Absolutely you could. But let's go on to the second guy. The second guy is, this is to the 1/2 power. I'm going to go right here. So the 1/2 comes down in front. This grouping, 12 squared plus x squared, goes to 1 less power, negative 1/2. But then I need to multiply that by the derivative of what's inside the parentheses. That's just a 2x this time. Ooh, 2's cancel. I can do that. 2's cancel. Cancel, cancel. So let me put my fraction together. My fraction has this in the denominator, 12 squared. Actually, it's a square root of 12 squared plus x squared. And in the top, I just am left with an x. So when you set this thing equal to 0 to figure out where that minimum is, that is one hot mess. So what you're going to do is go to your calculator, and you're going to put this in your calculator. Now you can continue to simplify this down more before you put it in your calculator so that there's less things in your calculator that you've got going on. But what you're going to do is put this into the solve menu. Make sure you put in the equals 0 and the comma x when you use the solve function in there. That's a whole lot of input, so I'm going to let you play with that, and I'm going to tell you that the answer you should get is x equals 9. That's what you're going to get when you put that in the calculator. So where should the stake be placed for this one? If you remember the picture, there's two buildings, a stake like this. Where should it be placed? One side would be, I think it was, they were 30 feet apart. So this whole thing is 30 feet. Well, one piece is 9. That means the other piece is 21. So that's your answer, 9 feet. And x equals 21 feet. Where should it be placed? 9 feet from one of the buildings, from the building. Okay, that's number 2 from section 510. Number 3 is totally different. Number 3 doesn't have any anything related to section 510, so number 3 is a little bit starting from scratch. A particle is traveling along the x-axis. Its position from the origin is modeled by this equation, where x is in centimeters and t is in seconds. On the interval from 3 to 9 seconds, find when the particle is farthest right. Farthest right is like taking a maximum. Farthest right is like a maximum value. Well, how did we find maximum values back in the last unit? And if you remember, we took the first derivative, so let's do that. F prime of x is going to be 3x squared, or 3, I should say t, right? F prime of t. I should actually say x prime of t. I want to put all my notation correct. There you go. X prime of t equals 3t squared plus minus 30t plus 72. All right, that's going to give me the velocity of this thing, the derivative of it. So x prime of t, I know that everybody's got a 3 in common. Take the 3 out. T squared minus 10t plus 24. And then I want to factor that thing, set it equal to 0. The 3 just gets ignored. Mr. 3 can't equal 0. T squared minus 10t plus 24 actually factors into t minus 6 and t, making that like a 6, t minus 4. So that means I get t values of 4 and 6. Well, maximum values mean that I need to find a table of values and use the endpoints, because maybe the endpoints just might be the maximum value or the minimum value. So when I set up my table of values like we did back in the last unit, I have a 3, I have a 4, I have a 6, and I have a 9. Now when I plug these in, I'm plugging them into, and this is really important to remember, the original function. I want to know what they are from the original function. So I'm going to put the original function in my y1, I'm going to go to the table and I'm going to plug these in, and here's what pops out. again, for sake of time. 99, 103, 99, and 153. So the question says, when is it farthest to the right? Well, the maximum value is down here at 9. So our answer is when t equals 9 seconds. Find when the particle is furthest to the right. It's furthest to the right when t equals 9 seconds. It didn't ask you what the maximum value was, so you don't need the 153. You just use that to be able to answer what time it was. The question was a when question. So when is it going to be a time? T equals 9 seconds. On the interval, same interval, what is the maximum speed? Now, maximum speed, I got to think about this a little bit. First of all, speed equals the absolute value of the velocity. I think you remember that. Speed is the absolute value. So what I'm looking for is the maximum or minimum, in this case, well, maximum. I'm going to leave it as I'm just going to leave it as max. Max of v of t. Well, now you got to think about this. This can be a little bit confusing. If I want to find a maximum, I need to take the derivative of that function, just like I did up here. If I want to find the maximum of the velocity, then I want to take the derivative of velocity, which means I'm really going to the acceleration, or the second derivative of x. Well, what's the derivative of that? Go back up here, 6t minus 30. When I want to find a maximum or minimum, I set that equal to 0, 6t minus 30. Factor out a 6, t minus 5, t equals 5. Did we answer the question? What is the maximum speed? We did not. First of all, I need to check the interval. I'm going to put my x and y table together here and see if the endpoints affect that, because sometimes the endpoints do. So I have 3, I have the 5 I need to check, and I have a 9. This one's not that hard to just, again, you're plugging it, well, you've already got the original in your y1. So go in and figure out 3 and 9 we know. Actually, you're plugging it into the velocity one. So now you need to put the velocity one in your y1 and then calculate it out. Because remember, we're going back a derivative to be able to do that. So this one gives you 3 gives you 9. y1 is this. 3 gives you 9. 5 gives you negative 3. And 9 gives you 45. Question wants to know what is the maximum speed. Not when did the maximum speed happen, but what is the maximum speed. So my maximum speed is 45. Let's think of the units on that. Speed would have to have some kind of units over time. So if I go back and look, I am centimeters and seconds, 45 centimeters per second, and that's your answer for this guy. Okay, so that takes care of the notes for this section. Let's do a couple practice problems together. Here's ones that I chose. Number 4 is first because it's different than the other ones that we've seen. Numbers 1, 2, and 3 are kind of similar to ones we just did. Like, look at this. Where's it farthest to the right? Where's the maximum speed? We just did a problem like that. Okay, so number 4 is the first one you come to that's going to be different than stuff you've seen before. This is a popular question. I've seen this on the AP exam before. This picture kind of thing. A rectangle is formed with the base on the x-axis and the top corners of the function on the function 20 minus x squared. Find the dimensions of the rectangle with the largest area. And you're like, what on earth? How am I going to do that? They're really not that bad. Let me show you. All right, first of all, I'm going to give you a picture. All right, think of what this looks like. This is an unhappy parabola that's up 20. So it's going to look like this. unhappy parabola, up 20. So what's happening is you've got a rectangle inscribed in here where the corners of that rectangle lie on your parabola. Find the dimensions of the rectangle with the largest area. Well, that's this area in here. You're talking about that area. Where can I put that where I'm going to have the largest area? All right, so let's not get too complicated. Here, this is 0, 0, right? So when I go from here to the edge where this is some x value, right? I've gone horizontally to here. That's an x value. Here's what it's kind of different with this. But I also have another value. That's x is just this little piece. I also have another part of my rectangle that goes from 0 to this x value. Well, this has a length. This would be to negative x, right? This has a length of x as well. And then my vertical distance is my y. So I'm going to think about what this coordinate value is. This coordinate would be, I'd be going x and I'd be going y. I'd be going x and then I'd be going y. Well, don't you know that y equals 20 minus x squared? So that means that the coordinate is x comma 20 minus x squared, my y value. Make sense? So let's look at, just in general, I'm trying to find the largest area. That means my maximum area. That means I'm finding the derivative of the area. So the area of my rectangle, area of a rectangle is length times width. In my case, the length is x and another x, 2x. And the width is the height. That's my 20 minus x squared. All right, so let's work our way through this. That's my area formula for this particular situation. So I am looking towards finding a maximum, which means I need to find the derivative. So I want to put this in a format where I can find the derivative, and that's my next task. So I've got 40x, just distributing the 2x, minus 2x cubed. Find the derivative of that. 40 minus 6x squared. Again, trying to find a maximum, set it equal to 0. 0 equals 40 minus 6x squared, or 6x squared equals 40. I mean, there's a lot of different ways you can do the algebra of this, but anyway, if I keep going in this direction, x squared equals 40 over 6, or 20 over 3. And so I need to take the square root of that to get the actual answer. So x equals plus or minus the square root of 20/3. Did I answer their question? I don't know. Let's go back and look. What are the dimensions? Find the dimensions of the rectangle with the largest area. Well, this guy here is, if my x is this, my dimensions, I'm going to put it down here. I have one dimension is 2 x's. Well, if I take my x and I have 2 of them, then I have 2 square root of 20 over 3. By the way, if I'm a dimension, I'm not negative. But it's interesting because you have positive 20 over 3 here, and this would be your negative square root of 20 over 3 I'm talking about. So these would both be square root of 20 over 3, so you'd have 2 of them. Could I write that prettier? Sure, I could do all sorts of things, but and I could even put it in the calculator and get a calculator decimal answer. But that's a story on that one. And then I have a y value, right? We said it was 2x times y. So my y value is, put in your square root of 20 over 3. Maybe I'll go up here and do this. 20 minus the square root of 20 over 3 squared. What happens when you square a square root? It gets rid of it. So now I've got 20 minus 20 thirds. If I want to subtract them, they need common denominators. This guy has a 1, he needs a 3. He's 60 thirds minus 20 thirds gives me 40 thirds. You can barely see me. That's my y value, 40 thirds. So my dimensions, and did they give me units on this? Nope, they didn't. All right, so 2 times 20 thirds is my length, and my width is 40 thirds, and that's the deal. So that was the first one that I picked. Here's the next one that I picked. Oh, by the way, we're going to start skipping things that are not things that are going to be seen on the exam so much. So numbers 6 and 7, they actually get pretty complicated. And in the midst of their complication, I don't think it's worth our while because I've never seen these on the exam before. So we are not doing 6 and 7. Okay. I'm going to number 12. And I think number 12 is the last thing we're going to look at. Because number 12 brings in a whole lot of stuff. This guy's got a whole lot of pieces to it. All from a chart. And talking about apple juice. Here we go. All right. Mr. Sullivan's making apple juice from apples he collected in his neighbor's orchard. The number of gallons of apple juice in a tank at time t is given by the twice differentiable function a, where t is measured in days from 0 to 20. The value of a of t is at selected times are given in the table below. Use the data in the table to estimate the rate at which the number of gallons of apple juice in the tank is changing, the rate of change, at time t equals 10 seconds. Show the computations that lead to your answer and indicate the units. Well, where's 10? 10 would be right in here. I don't have any values for 10. How do I find a rate of change, estimate the rate of change at 10? And so the only way that you can do that is go back to your f of b minus f of a over b minus a stuff. Find the rate of change, find the slope. And so that's what we're going to do. We're going to find a of 12 minus a of 8 over 12 minus 8. That's the rate of change. They didn't give me a function. I can't find a derivative, so that's the best I can do is give them the slope. Again, why they use the words estimate, and you saw rate of change kind of broken up in the verbiage of that. So here I go, 10 minus 9 over 4 is 1/4. Well, what does that represent? It is gallons, right? We have our y values on the bottom, so gallons per day. 1 represents my gallons, 4 represents my days. Cool. Got number 12a. For B, 0 to 12, for 0 to 12, is there a time at which the derivative is 2/3? Justify your answer. I don't know. Let's try it out. If I have 12, this is now going to be a of 12 minus a of 0 over 12 minus 0. Let's see where that takes us. A of 12 is 10. And again, I'm just using these endpoints. 10, a of 0 is 2 over 12. I get 8/12. What does 8/12 reduce to? Darned if it isn't 2/3. Now, do you remember what theorem justifies that? When you find the slope and it equals the derivative that they're giving you, it's by the mean value theorem. Yeah, the mean value theorem is what guarantees, as long as these numbers come out to be the same, when you estimate the slope, and they give you the 2/3 as well, when they come out to be the same value, then you know that it is going to work, that yes, you have that thing because of the mean value theorem. All right, here's where it gets a little bit more dicey and into the section that we're in right now. So far you've been A and B, and you're like, oh, this is easy, squeezy lemon, easy. The number of gallons of apple juice in the tank at time t is also modeled by this function. Now they're going to put a function value to it, where t is measured in days between 0 and 20. Based on the model, at what time between 0 and 20 is the number of gallons of apple juice in the tank an absolute maximum? Well, we just were doing that, right? If I want to find an absolute maximum, I have to take the first derivative, set it equal to 0, and make a table of values with the endpoints and what I get. Right? In theory, that's where I'm going. So that's what I need to do with this guy. I need to take his derivative. I've got okay. I'm just looking at my notes when I did it. I just didn't call it the derivative. Okay, b prime of t gives me 3. Oh my goodness. This gets complicated. 3/2 comes down times 1/2. One piece at a time, kids. 3/2 times 1/2, that's 3/4. The group has to go, t plus 4, to 1 less power. 3/2 minus 2/2, 3/2 minus 1, is going to give me 1/2. Times the derivative of what's inside. Well, luckily for us, that's a 1. And that's it for that piece. Go to 6. The derivative of 6 is 0. So that's what I've got. Now what I have to do is take that first derivative and set it equal to 0 to find the maximum. So I'm setting this equal to 0. And I'm going to take this thing, 3 minus 3/4, and I've got a t plus 4 to the 1/2 power. Okay, so here's where I'm going to go. I'm going to take this 3, I'm going to swing these things around so that they're on opposite sides of the equal sign. I guess what probably is best is if I take this guy who's negative and move him over so he becomes positive. Ultimately, you're going to have this. 3 equals 3/4. However you want to play with it, but to the 1/2. I'm trying to solve for t. So I've got to slowly break apart the things that are around t so I can get it by itself. So the first thing I want to do is multiply both sides by 4/3. I'll kind of put it out this way. 4/3. This guy needs a 4/3. Well, what does that mean I end up with over there, right? The 3's cancel out, so I've got a 4. 4 equals. My 3/4 and 4/3 cancel out. I've got t plus 4 to the 1/2 power. I'm trying to dig to t. This 1/2 power's got me all messed up. That's like a square root. So how do you get rid of a square root? Well, you square both sides. So now I'm going to square both sides. Squarey, squarey. Gives me 16 equals t plus 4. Now I'm into a nice little algebra thing. I can take 4 away. I've got 12. 12 is my t. Am I done? The answer is no, because remember it's a maximum value that I'm looking for. So I need to make a table of values with my endpoints of 0 and 20 and the t value I just came up with. Now where am I plugging it? I'm plugging it back into the original because I want to know what the y values are doing. So it's going into b of t. So in your calculator, you're going to put in y1, plug this in. You're going to get values out, I'll tell you. 0 gives you 2, 12 gives you 10, and 20 gives you 7.2. So, maximum value. Biggest number is 10. Biggest y value. And so the question is, again, at what time? They want to know at what time this happens. And so we say at t equals 12. T is measured in days. 12 days. Okay, there it is. Then the last question, D. For the function b defined in part C, the locally linear approximation near t equals 5 is used to approximate b of 5. Is this approximation an overestimate or an underestimate for the value of b of 5, and give a reason for your answer? Now, I don't know if you remember, but several sections back, a few units ago, we talked about, is something an overestimate or an underestimate? Do you remember what we looked at to determine that? Overestimate, underestimate. And the answer is that we looked at the second derivative. And if it was concave down, it was an overestimate because all the tangent lines would be above. If it was concave up, all of my tangent lines would be below it. So it would be an underestimate. And so this is bringing that topic back up again so that you kind of keep it at the forefront of your brain. So that's what we're going to do. We're going to go for the second derivative. I want to know what b double prime of 5 is. Is it positive or is it negative? Is it concave up or is it concave down? So I got to go back to my first derivative. I'm looking at this guy here. The derivative of 3 is 0, so I'm not going to get anything out of that. But I can definitely take the derivative of this part. Negative 3/4. The 1/2 comes down in front. Well, what does that look like? 3/4 times 1/2 is going to be a negative 3/8. Take the grouping to 1 less power. T plus 4. If I'm at a half and I take 1 away, I'm at negative 1/2. Times the derivative of what's inside. Well, what's inside is just a derivative of 1. So there I go. There's my second derivative. If I put a 5 in here, negative 3/8 times 5 plus 4 to the negative 1/2 power. All right, and I'm going to keep going. Negative 3/8 times 9 to the negative 1/2 power. Now you can do this in a calculator or think about it. 9 to the negative 1/2 power, that would be like 1 over the square root of 9. 1 over the square root of 9 is 3, which would then cancel with this 3. They would become a 1, so it really comes out to be a negative 1/8. Now, the fact of the matter is, all you care about is it negative or positive? You know that this is a positive piece. The negative just tells you it's in a fraction. And so a positive times a negative is a negative. So I know the second derivative is concave down. Therefore, concave down. And if it's concave down, think about what that looks like, right? We've got an unhappy kind of situation. All of the tangent lines would be above it. So this is going to be an overestimate. Give a reason. Because b double prime of 5 is negative. And there you go. That, my friends, is section 511. So shoot me an email if you've got questions on anything involved with that. One more piece. For section 511 on the mastery check, you are skipping number 1. Mastery check 511, skip number 1. Okay? I will see you in class. Have a good one.